Hi everyone, I'm meteorologist Royal Norman, and this is Sonoran Sky Live, a service of First Alert and Arizona's family. And we talk about all things weather and climate, even when weather and climate mix with baseball. That's right, one of my favorite things to do, watch a ball game, that's for sure. And we get to talk a little bit about how physics impacts baseball. We're going to talk with Alan Nathan from the University of Illinois, who is one of the early adopters, let's say, of the physics of baseball. Alan, how are you doing this morning? And thanks for joining us. We really appreciate it.
I'm doing fine and happy to be here.
Yeah, I'll tell you what, I read some of your stuff early on, and it was brand spanking new, and it really sort of lit the fire like, we can start explaining this stuff. It used to be, for whatever reason, the ball didn't get out of the ballpark, or the ball didn't carry, or, he didn't hit it solid or whatever. But by physics, you're able to start explaining what's happening on the ball field.
Yeah, we certainly know a lot just by applying laws of physics, but in addition to that, nowadays, the technological tools that we have for example, tracking the fly ball, are just incredible. It's incredible for baseball people who like to know all this stuff, and analysts who are trying to understand, whether a particular player has hit the ball well or not. But also for physicists like myself, who really are simply trying to understand the game.
So I'm assuming you're a fan of the game, and that was sort of got you to do that little crossover, being a physicist and just sort of trying to make sense of it.
Sure. I've been, I sort of like to tell people I've been a physicist all of my professional life. I've been a baseball fan all of my life, so even longer.
Okay, so you went to the University of Illinois. Are you talking to us from Illinois today?
I'm not in I'm in my home actually, but yes, I'm in Champaign, Illinois.
Okay, so because I grew up in the Chicago area, I always have to ask everybody that I meet from Illinois: Cubs, White Sox, or Cardinals?
Right.
Which team is yours? Which team is yours?
None of the above.
Oh, okay.
Okay. So if you look carefully over my shoulder, you'll see a little Red Sox hat, and you'll see a picture of Ted Williams. So I'm originally from the state of Maine. I was born there, spent my first 16 years there. So I grew up a Red Sox fan, and I continue to be a Red Sox fan.
You will be a Red Sox fan forever, just like I'm a Cubs fan forever, and folks are White Sox fans and Cardinals fans forever. It's just one of those things. It's where you grow up and where it happens. So you're talking about all the technology that we have now. When 20 years ago, you were sort of in the infancy stages of some of this. Did you ever dream we would be talking about spin rates and speed off the bat? I mean, instantaneous information as hitters and pitchers did their thing. Did that ever occur to you that we'd get that far?
Not really. So, beginning just about 20 years ago, roughly 2006 into 2007, was when the first ball tracking technology was installed at Major League Parks, the so-called PITCHf system. And as soon as I learned about it, I immediately jumped on it and sort of had an inside connection with a company, Sport Vision, that provided the technology, and we had quite a good relationship. They were able to send me data, and I could crunch the data and learn about all kinds of things like how air affects the flight of the ball and things like that.
Right. And how friction affects the flight of the ball. Like there was a home run boom, I'll call it that, in I want to say the 2017, 2018 sort of time frame that may even be continuing. And you did a lot of research into that. And was the finding just that most of the extra distance was because there was less friction on the baseballs?
Yeah, so that was, I think, the primary finding. Of all the possible things it could have been due to, it was that the ball simply carried through the air better. It wasn't because of the air itself changing. I mean, the air density, the temperature, or whatever. It was very subtle differences in the baseball that affects this, what you referred to as the friction. The thing, I call it air drag. You know, the fact that the ball, as it goes through the air, has to push air molecules out of the way, and that causes the ball to lose some of its energy, so it doesn't travel quite as far. And that air drag, in addition to depending importantly on the air density and the size of the ball, and the shape of the ball, but that size and shape doesn't change very much. But there are little subtle things having to do with the surface of the ball, primarily the seams on the ball, that actually has a dramatic effect on the flight of the ball.
So it seems like reading some of your articles that there is, let's say if you use I don't know how many baseballs they use in a baseball season, but you use tens of thousands of baseballs. Over that test of thousands and thousands and thousands of baseball, there isn't that much variability in the different baseballs. But it seems like, if I may have read this wrong, please correct me, baseball to baseball, like the guy throws out one ball and they throw in another to play, there could be more of a difference than you expect.
Yeah, I mean, that was really one of the fundamental findings of our studies when trying to explain the changes in home runs, that the difference, the subtle effects with the air flowing over the seams, there were differences from one ball to another. Now, there are some differences the pitcher can tell, for example, just by feeling the ball. As you point out, they asked for another ball, having to do with the height of the seams. So the height of the red seams on the ball can certainly make a difference. But there's even more subtle effects, and I'm not quite frankly sure we even fully understand to this day what those subtle effects are.
That is pretty amazing. All right, we're going to talk a little bit about ballparks, because I was telling Alan when I emailed him that having watched LA games, Dodger games forever here in Arizona, before we even had a team, you know, there was, I don't know if there's a myth about Dodger Stadium, but some people will tell you the ball will carry at night. Some people will tell you the ball doesn't carry at night. Some people will say it doesn't carry during the day. There's a whole bunch of rules that don't seem to be making it right at Dodger Stadium. What do you find with Dodger Stadium and baseballs being hit there? Is there a pattern that you can actually discern there?
So when you contacted me and you sort of posed this question, I have to admit that I had not looked into this before. But in the few days since you contacted me, I have looked into it.
Okay.
And so, you know, we have the information to be able to answer that question. So basically what the question you want to pose is this. Suppose the ball leaves the bat at a particular so-called exit velocity and launch angle. Does it travel further in Los Angeles than it does in any other garden variety ballpark? And so I looked at the data from the last two seasons, since we have all that information. And the answer that I have come up with is that it looks pretty ordinary to me. So, you know, even when you correct for the temperature, which is pretty well known,
right,
it looks pretty ordinary. That it doesn't travel particularly better or worse than, you know, pick your other favorite ballpark, other than Coors Field in Denver.
So what do you think announcers and players are seeing? Because just last weekend I was watching a game. The Dodgers were on one of the national networks, and I was watching the game. And early on they were like, "Oh, the ball's not carrying. They're dying. They're dying on, you know, on the warning track." And then all of a sudden they started popping them out, and they're going, "Oh yeah, now it's time. Now the ball." Is it just sort of they're trying to figure it out and they're just not quite getting there?
Well, I can't speak for them as possible. However, one thing that's very hard until recently, very hard to take into account with all the possible weather-related effects is the wind. Now, you look, if you're at a ball game, you look at the flags in the stadium. Look down the right field line. The flag is blowing at the wind is blowing at a certain speed. You can tell the direction. Now look on the other side, and you see the flag blowing in a different direction. So because the air has to pass through the stadium, okay, with all these different obstructions and scoreboards and concourses and whatever, both the speed and the direction of the wind could be different at different locations in the ballpark and at different times. And until recently, given the complexity of that problem, until recently, it's very, very hard to take wind into account, except in some, carefully well-defined cases. But now we actually have a better handle on it than we used to, due to some pretty innovative research that's been done.
That's cool. Alan Nathan is our guest. Coming up, we're going to talk about, after the break, we're going to talk about some of the I say they're easy things, but some of the more common things that impact baseball play and baseball flight and pitcher release, etc. We're going to talk about some of those, but also I want to remind folks that coming up, we're going to talk about Ted Williams' 502-foot home run and the red seat at Fenway. That is one of the most coolest baseball stories ever, so stick around for that as well when Sonoran Sky Live continues. Welcome back. It's Sonoran Sky Live, and we are talking about baseball, the physics of baseball, with Alan Nathan from the University of Illinois, one of the true early adopters of trying to figure out baseball and physics, and he has some great insight. Hey, Alan, I'd like to go over some of the, I'll call it the easier stuff, but some of the stuff that kind of might make sense to folks and doesn't make sense in terms of how far a baseball might fly or a bat could hit it. First of all, wind. You talked about that earlier. If you got a wind behind a baseball blowing out to right field and the ball's going to right field, what difference does a wind make? 1 mile an hour, does that make a difference? 5 miles an hour? Has that been quantified?
Pretty much, actually. Mm-hmm. So for a ball that's hit on, a typical home run trajectory, so 100 miles an hour off the bat, around a 30-degree launch angle, which is about optimum. If the wind is blowing up, so that ball will travel close to 400 feet in still air, okay?
Hmm.
If the wind is blowing out, that 400 feet goes up to about somewhere between 400, with a 5 mile per hour wind.
Hmm.
5 miles per hour is barely perceptible, okay? 5 mile an hour wind will make that ball carry an additional 15 to 20 feet.
Whoa.
It's incredible. I mean, so given that until recently, that was the major thing that we couldn't quantify very well, or simply because we didn't know the airspeed and direction at every point along the trajectory, which is what you need to know. My 15 to 20 feet assumes the air is moving 5 miles an hour out at every point along the trajectory, which it may or may not.
Right.
Typically up high, the wind has a higher speed than if you're at field level. But okay, if I might, there's a very interesting story that just happened a couple of weeks ago, and involved the Cubs, your favorite team. Ian Happ, the wind was blowing at about 30 miles an hour at Wrigley Field
Okay.
okay, and he hit a ball that, had there been no wind, would have traveled about 430 feet. It would have easily cleared the ivy wall.
Yeah.
It only traveled 320 feet. That's incredible. About 100 and more than 110-foot difference this 30-mile-an-hour wind made. So that was actually, you could do a Google search on it. It's been talked about a lot.
That is amazing. Now, what about the baseball itself? We have baseballs in Arizona, as you know, are in humidors. Do baseballs fly more if they're hot or colder, or does it matter? Has there been any studies done on that?
Yes. Just one point of reference, though. Arizona was the second team to employ a humidor.
Mm-hmm.
Colorado was the first. But since the last 4 years or so, every major league club stores their baseballs in a humidor.
Oh, okay.
So the humidor, if the ball were not in a humidor, okay, so consider a place like Arizona,
Mm-hmm.
where it's very, very dry. The relative humidity is really, really low. If you store the ball at, say, 70 degrees Fahrenheit, 50% relative humidity, it absorbs water. So the ball gets a little bit heavier. And this particular factor about the ball, the technical name is the coefficient of restitution. It's the bounciness of the ball.
Yeah.
Okay. And, a super ball is very bouncy. A baseball, not quite as, not as bouncy. When the ball absorbs water, that bounciness factor actually gets worse. So the ball is not hit as hard. And if it's not hit as hard, it's not going to carry as far. The fact that the ball weighs more also means it's not hit as hard. But there's an opposing effect, because a heavy ball will actually carry through the air better than a light ball. So there were two effects. The weight effect is sort of partially compensated, but not the coefficient of restitution effect.
Oh.
And so when balls are stored in a humidor, it affects their performance. Now, they don't affect every club in the same way. So consider Miami, where the atmosphere is very humid.
Yeah.
So when you store the ball at 50% relative humidity, you're actually increasing the coefficient of restitution. So it affects different clubs, different venues in different ways.
Oh, wow. All right.
But it certainly has an effect.
True or false, a ball hit to center field what's the word I want to say? A ball can be hit to center field harder than it can be, and farther than it can be to left or right field. True or false?
Harder, I won't vouch for, but further, yes.
Okay.
So for the same launch conditions, it actually carries further to center field than it does to either left or right field. And that's a very subtle effect, You have to really be into the weeds to understand it. But I actually studied it and wrote a paper on it and everything. But it has to do with the fact that the air drag depends on the spin of the ball. As the ball is spinning faster, the air drag actually increases, number one. And number two, there's more spin on the ball, generally speaking, when it's hit to left field or right field than there is to center field. And as a result, the ball doesn't carry quite as far.
Oh, so
it's not an enormous effect.
Yeah, but it's all about
it is an effect.
Once again, it's all about the spin. We could talk about this for hours, but we're going to take a break, Alan. Alan Nathan's our guest. We're talking the physics of baseball, and we're going to, I don't even know if we have time. We need another hour to dig down into the longest home run ever. Ted Williams, 502 feet, the red seat at Fenway. Did it happen? I think that it did, but we're going to talk to Alan about it in just a bit. Welcome back to Sonoran Sky Live. We are talking with Alan Nathan, University of Illinois, physics of baseball. We're going to get right to what is probably the greatest home run of all time, or maybe the longest home run of all time. Ted Williams, 502 feet at Fenway. What say you, Alan? Can you set up, there was a lot of weather going on that day. Can you set up what was happening that day in the weather world before Ted Williams hit that home run?
Yeah, so this happened in June of 1946, and the temperature was not, I don't recall exactly what the temperature was, but it wasn't anything special. What was special is that the wind was blowing straight out at about 20, 21 miles an hour. So the deal is this: Ted hits this long fly ball, and okay, there's a picture of it.
Yep.
And there's a guy in the stands way up in the bleacher section. His name is Joseph Butcher, and he's wearing a straw hat. And the ball hit him on the top of the head.
No way.
Broke his hat.
Oh, wow.
So, in fact, you see the hat in that picture there. And so people have been trying to, and since that's the longest home run ever hit in Fenway Park, and to commemorate it, the Red Sox management painted the seat red.
Right.
And that seat is still there to this day. It's a red seat. And when you look at it, you can't believe that anyone could hit the ball that far. So how far away is it? Well, it used to be thought to be 502 feet. And since the stands are rising, the ball actually hit the guy's head about 30 feet off the ground.
Oh, okay.
Now, so when you talk about the distance of a home run, usually you don't mean where it actually hit. What you really want to know is how far it would have gone had it not hit anything and got down to ground level.
Right.
And so you need a little bit of physics to make that extrapolation. But my guess was around 538 feet.
Oh.
But it was wind aided. I mean, without the wind, it would have traveled 90 feet less, something like that.
Yeah.
Now, there's actually been an update to this. So the guys from Major League Baseball have used a fancy device called LiDAR to measure very carefully the distance of home plate to that seat where the ball hit. And it's only 496 feet. So, all right, we have to subtract 6 feet off that distance. But it was it was one heck of a long home run.
Yeah.
And it was a fun exercise for me, actually, to try to estimate how far it would have gone had it not hit the guy.
So it went you believe it went the 502 or give or take or whatever. I know there are some doubters, but one of the things I also noticed when I was flipping through the history of that, Fenway did not have that upper deck, that area now where they have a lot of the media and that upper deck. So Fenway was a lot flatter so that wind could get in there and get into baseballs more than it can now.
Absolutely. And that fly ball, that home run of Williams benefited greatly from the wind. It would have benefited less, I'm guessing. I haven't tried to figure this out, but almost surely would have benefited less with the current version of Fenway Park with the press box rising behind home plate.
Right. And there's a lot of, then here we have a split screen. On top is the current configuration, and on the bottom is what it was circa Ted Williams' home run. So, yeah, there was a lot less in the way of the wind in those days.
Right.
Yeah, so certainly could be one of the reasons for that. I just feel like that's one of the fun baseball stories and all. Now, before I let you go, I got to talk to you about Chase Field a little bit, our field here. One of the things we're very proud of, I believe, and I said this in a text and then I double checked. We are elevation-wise the second highest elevated airport baseball field in the United States at a little over 1,100 feet, or give or take a few feet, second only to Coors Field up in Denver. Now, elevation, even 1,000 feet, matters, doesn't it?
Oh, it matters a huge amount. So Coors Field, which is a mile high, over 5,000 feet, the air density is about 80%, 82% actually of what it is at sea level. And the Coors Field effect is enormous. A fly ball that would travel 400 feet at sea level under the same launch conditions, air temperature and stuff, would travel about 25 feet further at Coors.
Wow.
Now, not as much. So, 25 feet, let's call it. So Chase is 1,000 feet, or 1,100. So it's about a fifth.
Yep.
So it would travel maybe a fifth of 25 is 5. So 5 is sort of maybe a 5 or 6 foot advantage that Chase Field has. Of course, they would have an even bigger advantage if they opened the roof.
Yes.
Because then it's very, very hot.
Yes.
It would also be quite unpleasant, but it's very, very hot, and the temperature effect would add quite a bit.
Well, and they have some panels too out in the outfield that I want to say it was Curt Schilling, it might have been Randy Johnson, never wanted those panels open when they pitched because they thought that funneled in air and made a chute that was kind of pushing baseballs out. So yeah, it's like every baseball field you go to, you can find something that's really interesting. Alan Nathan from the University of Illinois, he's the man. Physics of Baseball. Alan, it was great talking with you. Thank you very much. Folks, go out and Google him, get his books, read his articles. They're fantastic stuff. Alan, you have a great day.
You too. Thanks for having me.
Everyone.